Today we're going to be solving the 3.1 to 3.10 physics periodic course practice quiz, and let's start. So first question is asking us which of the following materials are magnetic, and we have a list of materials. Carbon, if you look at your periodic table, you're going to see that it's non-metal أصلا, so it cannot be magnetic. Cobalt is a metal. It's found in the transition metals on the periodic table, so yeah, it's magnetic material. Sorry. Iron oxide powder. We know iron is also a metal that is magnetic and has magnetic properties. Aluminium is a metal, and so is silver. Both of these are metals, yet none of them are magnetic. These I prefer like you memorize that aluminium is not magnetic nor is silver. So that's that. Now let's move on to the next question. So, which of the following statements describe magnetism are true? All ceramics are ferromagnetic? No. If you read the book, it clearly tells you only some of them are ferromagnetic. Permanent magnets retain their magnetic properties indefinitely. So, indefinitely, it means like for only for like an unspecified period of time. So, which is false because they retain their magnetic properties forever. So this is wrong. Magnetic properties of the permanent magnet can be lost through strong heating. Yes, of course. Magnetic forces are action at a distance forces. Yes, you don't have to actually touch the things together to have a magnetic force. Magnetic forces are interrelated with electric forces but not gravitational forces. What this is telling you, it's like that magnetic forces are like electric forces but not like gravitational forces. This is also true. Now, let's move on. What's true about magnetic field lines? So every line starts at the magnet's south pole. This is wrong because it starts at the north. Now, they never cross each other. Yes, they will never ever cross each other. They are imaginary and smooth. Yes. They always end at infinity. No, they end at the north pole. They end at the south pole. And they are imaginary lines along which the magnetic field vector points at any point. Yes, this is because they point at... This is just a memorizing one, you can't really understand it. Which of the following are ways to demagnetize a magnet? So, place a magnet in the freezer? No. It's only heating it that will make it loose, not cooling it. So this high temperatures, of course. Place a magnet next to a strong alternating current source, yes. And then store a magnet with soft iron keepers. No, that's gonna help you retain its magnetic properties. Knock a magnet with a hammer, of course. It's gonna like decrease its magnetism or demagnetize it. Now, which of the following actions would demagnetize a magnet? Again, keeping it in a dry place doesn't do anything. Storing it at room temperature will also not do anything. Dropping it might demagnetize it. Without a soft iron keeper, yes, it will demagnetize it. And an alternating current in an electromagnet will definitely demagnetize a magnet. Now, next question. The term magnetic field describes the property of the space around the magnet. This is just a definition you have to memorize. If the plotting compass is placed at point A and it's pointing rightwards, the direction of the magnetic field is rightwards. If it's the direction of the magnetic field at any point is the direction of the plotting compass. Now, the magnitude of the magnetic field created by a current carrying wire at a given point is directly proportional to the current in and inversely to the distance from. So if you increase the current, magnetic field will increase. If you increase the distance, magnetic field will decrease. Next question. The poles of a ring magnet are located on its flat side. So if you have a ring magnet, the poles are going to be on here and on the bottom of it, like here, not on the sides. But of a horseshoe magnet, the ones like this, it's going to be on its free ends, which is the same thing as saying its poles. Here, grade 4 science, grade 2 science even. N and S attract since they're attracting here. S and N are the opposite because this one's S, this one's N, this one has to be S, and if they're attracting, opposites attract, same repel. This is the broken magnet theory. It's telling you that if you cut it here, which of the following will be the answer? So if you cut it there, but at this point, then if this was N, this must be S, and if this was S, this must be N, which is the answer. Now moving on. Explain how to magnetize a hard magnetic material by stroking. So first you have to look at the picture. So here's the North Pole. It looks like if it's going in this way, that means that the North Pole is stroking this side, and then the South Pole would stroke this side, or either way it will be stroking this one. So that means that making the left end would be north, and whatever is left would be the south. So that's how you magnetize it with stroking it. A small iron needle used to determine the direction of the magnetic field is a plotting compass. This isn't anything new. Another way to say that the magnetic field as vectors is they obey the principle of superposition. Memorize it. It's what they obey. The direction of the magnetic field at a point of direction is the force it produces on the North Pole. Again, memorize. Okay, so for this question, it's telling you when a magnet is placed 10 centimeters away from a plotting compass, C, the force by the magnet on the compass is 20 millinewtons. The direction of the force on the compass, so we know that it goes from inside the magnet, it will go from the south to the North Pole, but from outside the magnet, it will go from the north to the south in this way. So the direction on this magnet, on the compass, is gonna go, since this is still on the way right, it's gonna still go right. But when you put it here, it's gonna go like this, and then like this, and then like this, and then like this, when it reaches back here. Now, here you have two magnets, and they have both the N on this side. That makes them repel, right? So whatever you place in between them is gonna repel. Because look, it's gonna go like this, and it's gonna repel the other one. They're going in opposite directions, so nothing is gonna come here making it now 0. It's gonna cancel out each other since they're repelling. The diagram below shows a single magnetic field line. If a freely suspended small magnet is placed at point 1, then it will orient itself tangent to the field line, like this. It won't go like this or whatever. It's gonna go tangent to it. The point 2 in the magnet is we always said it will start from its North Pole and go towards its South Pole outside the magnet. Since the direction is like this, then it must be going towards its South Pole. The pattern observed in the figure is the flux pattern. Memorize it. And which of the following statements are true? The poles neutralize each other in the air gap. No, they definitely don't. The arrangement of the iron fillings can identify the poles of the magnet. No, all you can see is the iron fillings making a shape. But can you tell where are they going from and where are they going to? No, it's just making the shape. So you know there is a magnetic field. It's the strongest between the poles, of course. The magnetic field between the poles is uniform, also of course. And that the arrangement of the iron fillings shows the direction of the field lines. No, it can't. Look in the picture. Here it's not showing you any directions. It's not telling you where is it going from, where is it going to. All you can see is it moving. So yeah. Now next question. So the diagram below shows field lines between the poles of a magnet. Several points are labeled. Pole X is, since you could see the flux pattern is going away from each other, they are not touching, then this must be repelling, this must be north. Any plotting compass placed at label point 3 will retain its orientation because there is no magnetic field to affect the compass other than the Earth's magnetic field. So, question 17, the magnetic field is, whenever you have an iron bar and a magnet, it's always gonna make all the magnetic fields go inside the iron bar and go out because it doesn't want it to obey a normal magnetic field. So we call it shunting, which means bypassing. The strongest magnetic field is observed at point 4, which is closest to the magnet and to the iron object, or iron bar. Now let's move on. Explain how to magnetically shield an sorry, I'm reading the other question. A sensitive compass needle needs to be protected from an external magnetic field. The best way to do it is store it in a case made out of soft iron. You have to make it out of a soft metal, the one that does not get it does not become a permanent magnet. So, okay, whenever they tell you axial, symmetric, radial field, you always have to choose the rings, because it's like the loudspeaker, the same thing they use in the loudspeakers, as you can see in the next part. None of these have an axial, symmetric, radial field. But here, when they ask you for plane symmetric, you're gonna choose any type of magnet with a little hole in it. This is used in the ammeter, in the electric motors, and those were current meter, which is the same as an ammeter, and the electric motors. These are the examples given in the book. These are the only two I think you should memorize, since they're the only two given in the book. Okay, this is telling you how to store magnets safely. This is a soft iron keeper. S will be to N, N will be to S, and then again S to N, N to S. Now the gray bars placed on the top of the bottom of the parallel magnets are called keepers, and they're made out of soft iron. Memorizing. Okay, for this question, you need to do the right hand grip rule. What the right hand grip rule is telling you to do is, look at this. This is a X in the middle. What does an X mean? X means that it's going into the plane of the page. So what you do is you take your thumb and you point it towards the tablet or towards the computer in the exam, and then see which direction do your fingers curl. If your fingers curl counterclockwise, if your fingers curl clockwise or counterclockwise, since this is going into the page, then it will curl clockwise. So your thumb on the point towards the page and you curl your fingers. Then you're gonna discover that your fingers are curling in this way. So then you will take the ones that obey the way your fingers are going up, then right, then down, then left. If it's going into the page. If it's going out of the page, if they show you in the middle this, then your thumb is pointing towards up, outside the computer, not towards the computer, no, opposite. And then your fingers are gonna curl in the opposite way. So yeah, so you could use the right hand grip rule, is what the thing I just explained, or Maxwell's screw rule. I rather you use the grip rules because we can't bring screwdrivers with us into the exams. Unless you can, then be my guest and use the screw rule. The explaining of how to do it is in the book. So here we have two parallel wires carrying equal currents in the same direction. So since they're two parallel wires and carrying equal currents, that means they're carrying it's like they're carrying north and south. So the point between them, it's gonna neutralize. There will be no force. And this point is closer than this point. That's why the magnetic field at B1 is stronger than the one at B3, because it's closer to the current. And B2, it's gonna be null or zero because it's between two opposite or same charged wires, you could say. Think of it like that. Now part B is telling you it's the magnetic field at point 1 is out of the page. How do you know? You put your fingers in the direction of the magnetic field, or the direction of the current, my bad. So the current is going up. So you put your fingers up, going forwards, and then you curl your fingers and just see which way is your finger. If your finger is pointing upwards, like a thumbs up, then it's out of the page. If your fingers are making a thumbs down, then it's into the page. Now, they're asking you which of the following are hard or soft magnetic materials. The needle of the plotting compass, whenever you read it in the book, it's going to tell you that it's a hard magnetic material because it gets affected by all magnetic fields. So it's a hard magnetic material. The speaker coil is a soft magnetic material because it's one of the examples of soft magnetic fields. You really see it in the book. It's soft because you don't always want it to be a magnet. Only when it turned on do you want it to be a magnet. Refrigerator magnet, the ones you stick on your fridge, if you remove them off the fridge, they're gonna still be magnetic. They're not soft, they're hard magnetic materials. Magnet keepers are soft magnetic material because if you remove them off of the magnet, they're not going to be magnetizing. You cannot use them as a magnet when they're off of the magnetic bars. Now, next question. Okay, like I said, not even grade 3, grade 2 math. North, north, south, south, repel. South, north, north, south, attract. North, south, south, north, attract. Like repel, opposites attract. Now, here again, same thing like I said before, it's the exact same thing. Your finger, put it into the page because here it's going into the page since it's an X. Curl your thumb will go into the page or point towards the screen, and your thumb will curl towards, the magnetic field is going towards the way your fingers are curling, which is gonna be in a clockwise motion. Now, next question. Hard magnets are hard to magnetize, that's why they're called hard magnetic. Soft iron, the name kind of gives you the type of magnetic material it is. Used in permanent magnets and compass needles, hard since they're permanent. Hard steel, like self-explanatory. Easy to magnetize but readily loses its magnetism, so it's easy, so it's soft. Whenever they tell you hard to magnetize, it's hard. Whenever they tell you easy, it's soft. Okay, out of these options, glass is not even a metal, nor is wood. Nickel and steel are both metals that get magnetized. Here, definition. The magnet attracts an object made out of ferromagnetic material. The latter behaves like a magnet. So if you bring a magnet towards iron, even though iron itself is not a magnet, it will act like a magnet. It will repel and attract. So this is called magnetic induction, where when you bring a magnet close to an object, the object will start acting like a magnet. It's like as if the magnet is giving it some magnetic properties. Okay, here S to N and S to N. So at A, it's going left. At B, it's going into the N, so right. At C, it's going left. And at D, it's going into S, because we know that inside a magnet, they will go from S to N, from outside N to S. So whenever it's at the poles, it's gonna be moving rightwards, B and D. They're both gonna be moving rightwards, but A and C, they're gonna be moving leftwards. So yeah, that's it for this question. Now let's move on. Okay, for this question, it's really easy. You have two magnets here and here. Both of them are repelling each other. So whenever you have repelling, whatever point is in between them is the last one. Whatever points in between them, because it has the weakest. There is no attractive forces here. So then you put this one as the last one immediately. But then you know that it's gonna move from N to S. Like this. So B is gonna be the strongest since the point is coming, it's like straight outside of N. Like it's the closest. Then C and D is the furthest, making it the third out of B, C, and D. And that's it for this quiz. Hope you understood everything. Have a good day. Bye.